Hey AP Chem, we're going to have a discussion about the collection of a gas over water experiment. We're going to do it in a simplified form instead of having a separate tube that pumps water into our collection device. We're just going to do the whole reaction in this collection device right here. So this is filled with some hydrogen peroxide, and I'm going to put in a little cage full of manganese in here, and what the manganese does is it catalyzes a reaction that decomposes the peroxide, and so when the peroxide decomposes, it's going to decompose into water and also hydrogen gas. So we should start to see some bubbles, and hopefully we'll get enough bubbles going where it'll actually displace a bunch of water. I'm going to invert it into this graduated cylinder here, and we can hopefully see some displacement. So let's see how this works out. Ooh, that was pretty smooth. Okay. So you can see that I didn't lose a whole bunch of water, so hopefully anything you see bubbling up is going to be the hydrogen peroxide mixing with the manganese. You can see my contraption here at the bottom. I'll just clear away some of these bubbles so you can see it more clearly. You can see the cage there. You can see a whole host of bubbles that are going up, up, up. So we'll just let this sit and run for a little bit and see how much gas we can collect. Alright, so it's run far enough. We're going to stop it and then we'll look at it a little bit. There we go. Okay, so we've collected hydrogen gas in this tube through the water. So I want to look at the hydrogen gas inside the tube and kind of talk about pressure and forces that are going on here. So, for starters, we have at least two different forces going on here. So here you can see the level of the water that's still, or the hydrogen peroxide that's still in the tube. You can see the level of hydrogen gas, and you can see that the water here is open to the atmosphere. So for starters, let's talk about the forces that are going on. If I hold, depending on where I hold this, we have a couple different forces happening. So let me hold it here, and let's see, so the level of my hydrogen peroxide is here. Let's see if you can name 3 different forces that are going on in this system right now. This would be a good time to pause the video. So 3 different forces that you should be able to identify would be the force of the atmospheric pressure on the surface of this water. So all the gas in the atmosphere is colliding with surfaces that it comes in contact with. And one of the surfaces is going to be this open bowl of water here. And so we have the atmospheric gas pressure pushing down on the surface of the water. And when the atmospheric pressure pushes down, it tends to push this water down, and the water escapes up in this tube. Another force that you should have been able to name would be the column of the hydrogen peroxide. So gravity is working on this column of hydrogen peroxide molecules inside our glass tube, and it's pulling it down. So one of the forces is gravitational force on this column of peroxide. And then the third force is going to be the pressure of the hydrogen gas inside this tube. So the pressure of the gas pushes down, just like atmospheric pressure pushes down on the surface of the peroxide in the tube. And the pressure of the gas in this tube is going to push down, and if it pushes down hard enough, it forces the water or the peroxide out the bottom of this tube and into this container. And that's what we saw happening. As the gas pressure built up in here, it actually forced some molecules of solution out the bottom of the tube and onto my counter. So we have a couple different forces happening here. Now the other thing I want to talk about is what gases are up here. We talked about how we collected hydrogen gas. Is there any other gas up there? This would be a good time to pause the video and think. And the answer is yes. There is another gas up there. So what we filled the tube with was a solution of hydrogen peroxide. The bottle says it's about a 3% solution of hydrogen peroxide. That means 3% of the molecules are H2O2. What's the other 97%? It's water. The other 97% of this solution that you're buying at the store is just water. And so what we have inside this tube, what we filled this tube initially with, was hydrogen peroxide and water. And as we talked about earlier, anytime you have a solution of something that is volatile or willing to evaporate, some of those liquid molecules are going to be pulled up into the closed container, and they're going to establish a vapor pressure. So we have some water molecules up there too, establishing a vapor pressure. Now it's possible we have hydrogen peroxide molecules establishing a vapor pressure also, but we're going to ignore that for now and just pretend that we have hydrogen gas and water vapor establishing a vapor pressure in the closed container of our tube. Okay, now the other thing I want to show you, is the level of gas in here. Now, I'm not sure if you can see that, maybe a little bit. Look what happens when I do this. Can you tell? The level of solution in my tube actually bounces. I can get it to bounce. I can get it to bounce under the water. I can get it to bounce above the water. Now, why does it do that? It bounces because gas is really easily compressible. I can, just by a little thrust of my wrist, I can push the solution up and it actually condenses the gas. And then gravity pulls it back down and it actually expands the gas. So that's how easily gas expands and contracts. Not a whole lot of force necessary in order to get it to do that. Okay, thinking about our forces, can we know any of our forces? Can we know atmospheric pressure? Can we know the weight of the gravitational, the weight, which is the gravitational pull on this column of water, or the pressure of the gas inside our tube? Can we know any of those forces? This would be a good time to pause the video and think. Now, the easiest force for us to know, we can't know any of those forces just by looking at our system. We have to do something. We have to go look it up, or we have to calculate it. But the easiest one for us to go find is actually atmospheric pressure. We can just go look it up. If I type in atmospheric pressure, McMinnville, Oregon, let's see what it brings up. Okay, so I can go to NOAA for McMinnville, and I can get a pressure for today. It says 29.43 inches of mercury. Now, 29.43 inches of mercury is kind of a strange unit for us to use. 29.43 inches of mercury in millimeters of mercury. But it's easily converted. So that is 747.5 millimeters of mercury. Let's see what it is in atmospheres. If we just divide that by 760, that will give us atmospheres. 0.984 atmospheres. So today, the atmospheric pressure in McMinnville, Oregon is 0.984 atmospheres of pressure. Jenna, we just know one of our three forces just by looking it up. If you have a barometer on your wall, you can look it up that way too. Or you can just type it in, and chances are there is a weather report from someone somewhere that tells you what your barometric pressure is for today. You may have to do some conversions because, again, units that are convenient to us in chemistry with the gas laws are not always convenient to other industries. Okay, so 0.984 atmospheres of pressure, that's a point of data you want to write down. Okay, now what else can we know? So you may have mentioned that we could know the gravimetric pull of this column of water, or this column of solution. And we probably could, but we'd have to calculate it, which is going to introduce some potential error into our circumstances. And so what we want to think is there a way we could eliminate one or three of our forces? Can we manipulate our experiment somehow and eliminate one of our forces? So before we talk about how to do that, I want you to tell me about the system right now. Okay, so if my level of solution is right here, okay, so tell me what is equal to atmospheric pressure at this point in time. See if you can pause the video and write down an equation. And the equation that you should have written down is the atmospheric pressure is actually supporting the pressure of the gas and the column of water right now. So our equation would be atmospheric pressure equals our other two forces, pressure of the gas and pressure of the column of solution. Now, how does that equation change if I take this level of solution right here and I move it under the water level? Now, what's the equation that involves those three forces? Again, pause the video and see if you can write that out. And what you should have said now is that the atmospheric pressure plus the column of water, that is the difference, is going to equal to the pressure of the gas. Or you could say, you could just flip it to the other side and subtract it. That would work too. Okay, but at this point in time, since our level is under the level of the atmospheric pressure, it's actually atmospheric pressure plus this column of water is equal to pressure of the gas. Okay, so coming back to our original question, how can we manipulate our experiment to actually take out one of those three forces so that we don't have to worry about it, we don't have to calculate it, we don't have to look it up at all? Can you think about how to do that? And the only of the three forces that we can manipulate and we can actually eliminate by our manipulation, we can't eliminate the atmospheric pressure, we can't eliminate the gas pressure, we can eliminate the column of water though. So here we have a column of water, here we have a column of water, but if we move this so that our two surfaces line up exactly, the surface in the graduated cylinder and the surface in our little tube, we no longer have a column of solution to worry about. We don't have a column of water to worry about. All we have is atmospheric pressure and gas pressure. And so at this point in time, they should be equal as long as the level of water in your tube is equal to the level of water in your bowl, or in our case, a graduated cylinder. You don't have a column of water, and the other two forces, atmospheric pressure and gas pressure, are then equal. So that's how we manipulate our experiment. So what is the pressure in our tube right now? It is the same as atmospheric pressure, which is 0.984 atmosphere. So we now have the pressure of gas total in our tube, and we can look up what our water pressure is at our specific temperature. We are at 25 degrees Celsius right now. And then using those two, we can actually isolate what the pressure of the hydrogen gas is and figure out how much hydrogen gas we made. So those are all your considerations when you are looking at collecting a gas underwater. So it's important to kind of evaluate your forces and to know what the gases are that you're looking at. So good job today. I'll see you in class.